Welcome everybody to Algebra 2, Section 8.1, Measures of Central Tendency and Variation. So let's define that, measures of central tendency. So it is a value that describes the center / middle of data. And we're going to talk about three main centers or measures of central tendency. And the first one that we'll talk about is mean, which can be X bar, or sometimes it's also used as this little shape, which is called mu. Looks like a U, but with a tail on the left-hand side, or a long tail on the left-hand side. And this is what we know to be the mathematical average, or the arithmetic average. And that's found by adding all the values up and dividing by however many there are. Next is median, which does not have any sort of shorthand or abbreviation, except for maybe MED at times, I guess. And that is the middle value, and so that is found by lining all of the numbers up, or the values up, least to greatest, and then finding which one's in the middle. And if there are two terms in the middle, you average those two terms together. And then last, mode or modes is the most repeated value. Now, it is possible that there is no mode, and that is if every value is listed exactly one time, there would be no mode. And so here on data set number 1, we're going to find the mean, median, and mode, or modes for each set. And so number 1 here, in order to find the median and mode, it's easiest to list them least to greatest, especially for the median. So the lowest is 46, and then, 35 rather. Then I'm going to lightly cross it out to show that I've used it, and then that way I can keep track of what I've done. And then 46, 51, another 51, so I write it again. That'll come into play with the mode and the median, knowing that I use mode and actually the mean. Then 53, 58, 58 again, not 85, 59, 60. And so if I just add up all these numbers, we end up getting 471 and divide by 9, since there's 9 of them. So we say n equals 9 because there's the number of them at number n equals 9. We end up getting 52.3 repeating. So we say the mean is 52.3 repeating. The median, or the middle number, would be 53 then. So there's 4 lower than it, 4 higher than it. So 53 is our median. And what occurs the most frequently? Well, 51 and 58 both occur twice. So 51 and 58 are both modes, because they both occur twice, and no number occurs more than that. And now we'll do the exact same thing for number 2. So we'll order these least to greatest. So starting with 7, and then proceeding to 10, and then 11, 15, and 15 again, and 19, and 21, 24, 24, and 24, 27, and 31. And so as we calculate the mean, we end up getting 228 over 12 total numbers, which is 19. As we look for the median, Since there's 12, there's not a middle number, but there's 2 in the middle, and so we take 19 plus 21 and divide by 2, which would end up being 20. And then modes, so 15 occurs twice, but that doesn't matter because 24 occurs 3 times, so 24 is our only mode. And so now we're going to do the same exact thing for 2 different doctor's offices of finding the mean, median, mode for each of these, and I'm going to let you do them, and then pause the video, and then come back and see what I got, and just compare them. So doctor's office A, the mean ends up being 22, the median is 20, and the mode is 24. And this is already listed least greatest, and the same will be for the case for B. So on B, the mean is 16, median is 18, and the mode is also 18 here. And so definitely would rather be a patient at doctor's office B as far as wait times go. Don't know necessarily if they're better doctors there, or not, but better wait times. Don't have to be as patient to be a patient. Now let's talk about box and whisker plots. The box and whisker plot is a way to display these measures of central tendency. A way to measure the data, I should say. A way to display the data. And so what happens is our median goes in the middle of this box. And so our median, or what we call quartile 2, is in the middle of the box. And as we have our data here, we also have this thing called a minimum and a maximum in a quartile 1, or lower quartile, and a quartile 3, an upper quartile. And let's define some of these words, okay? So we have this word range. Okay, well, what's range mean? Range is defined as the max minus the min. What is max and what is min? Well, max is just the highest value, and min is just the lowest value. And so we put our highest value here, our lowest value there for our box and whisker plot. And then interquartile range. Well, before we get to that, actually, let's first talk about quartile 1 and quartile 3. So quartile 1, that's defined as the median of the first half of the data. So you separate the data into 2 halves, and you say, okay, of this first half, where's the middle? And of the middle of that first half, you call that quartile 1, or the lower quartile. And quartile 3 is the same idea, so it's the median, but rather than being the median of the first half, it's the second half. Of the data. And it'd be right there on the box whisker plot. So you got your actual median right here, and then halfway between the median and the minimum, you have your quartile 1, and halfway between your median and the maximum, you have your quartile 3, is the idea. And that's not necessarily going to fall halfway between value-wise. For example, you're not just going to find out where it's like, 0, 25, 50, or I should say 0, 50, 100, and you're going to have like 25 and 50, to where it's like, oh, exactly half of 50 is 25, and exactly half of, it should be 75 rather, half of 100, halfway between 100 and 50 is 75. That's not what we're talking about necessarily, but as far as half of the data values, counting-wise. So for example, on our last page, if we were to divide them out here, and we say, okay, the first half of the data, sectioned off here, quartile 1, here, quartile 3, here, quartile 2, that kind of a thing as far as sectioning off, as far as halves in quartile 1, quartile 3. So now, interquartile range, that wasn't actually finding the numbers and seeing what they were, that was just kind of a rough visual idea, to be clear. We'll actually go over how to find the numbers in a moment. So interquartile range, the measures of variation here. So this is just quartile 3 minus quartile 1. So this is the length of the box. So this is saying the right side of the box minus the left side of the box. The bigger number minus the smaller number. So it's the same idea as range, it's just inside the box, inside the quartiles. And thus you have your box and whisker plots. So the box is in between the quartiles, the interquartile range, and the whiskers are everything outside those two quartiles through the minimum and the maximum. So here we're going to draw a box and whisker plot of the data and find the interquartile range. Determine if the data is skewed or symmetrical, which is an idea we're going to have to talk about once we draw the box and whisker plot. So first, we actually need to establish this data as far as least to greatest. And so let's go ahead and write it down. And so our lowest number here is 2, and we're going to again have 2 of them. And so 2 and 2. And then we're going to have 2 3s. So 3 and 3. And then 1 4. 5 and 5. And then a 6. And then 1 7. And then 3 8s. Which would matter if we're doing a mode, but we don't need a mode for a box and whisker plot. And then 2 9s. And then it jumps up from 9 over here to 12. That's going to impact this later, and we'll see that. 13, 14, and 15. And so now, in order to draw our box and whisker plot, we need to establish, okay, how many numbers are there? So that way we can figure out where our median, quartile 2, is, and where our quartile 1 and quartile 3 are. Okay, so if we count all the numbers here, we can say, okay, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 numbers, okay? So that means our median here is going to be between numbers 9 and 10. So our median here, quartile 2, we right here, making it 8.5, okay, or 7.5. So quartile 2 is 7.5, okay? And so quartile 1 will be the first half of the data, which is going to be, so we said there were, 18 numbers. So the first 9 of these numbers, we're going to have, let's see, the first 9 of the numbers, splitting it there, we're going to have 5 of them in. So that means 4 is our 5th number, which should be quartile 1. And then 9 in the back half of our data, and the second half of the data, would be 5 of them. Halfway through that would be 1, 2, 3, 4, 5. This 9 right here would be quartile 3. And so we have quartile 1, quartile 2, quartile 3 there. Like that, and that's how we find the quartiles. And so now we can draw this box and whisker plot. And so what we can do is we draw a number line. And we'll do 1, 2, 3, 4, 5, 6, 7, 8, 9. And you want to try and make these tick marks as consistent as possible. I know mine aren't perfect. They don't have to be perfect. You just want to make them as consistent as you can. And holy cow, I made my number line way too big. That's okay. That's the least of my concerns. I can always make it smaller. And so, hey, look, my number line's smaller now. And that's okay. There are worse problems to have than needing to make my number line smaller. And so, I tend to either make it way too big or way too small. So, oh well. And so now, I can make my box, my middle of my box goes at 7.5. And then my start of my box is at 4, my quartile 1. My end of my box is at my quartile 3 at 9. And so then I can draw my box here connecting quartile 1 to quartile 3, and going through quartile 2. And then I need my whiskers, which go from my minimum to my maximum. And my minimum here is at 2, which I really only actually needed to go to 2, then not to 1. And my maximum is at 15, so I need to go to 15 here for my other whisker. And so now I have this box and whisker plot. And so we successfully drew it. And so now we can find this inner quartile range is what it asks us to do. So the inner quartile range, or we can abbreviate to IQR, because I'm lazy and I don't want to write out inner quartile range, IQR, interquartile range, or equals 9 minus 4, the quartile 3 minus quartile 1, big minus small, and that is 5. So we found interquartile range. And then the other thing it wants us to do is determine if the data is skewed or symmetrical. What does that even mean? Okay, well, symmetrical means that it's, even on both sides, or it mirrors itself. And so that would be the case where, a box and whisker plot would mirror itself if it looked something like this. To where, there's an even amount of whisker on this side compared to this side, and quartile 2 is about halfway between quartile 1 and quartile 3. None of that has to be exactly 100% perfect, but, close to each of those. And we can see here, quartile 2 is much closer to 3 than 1. And the box is much closer to the left whisker than the right whisker. And that's because it jumped so much from 9 to 12. And so many of these numbers are so much smaller than the few that are bigger. And so because of that, we would say the data is skewed. So now we can move on to where we have an established box and whisker plot. And we are going to find some information from this. So we're going to find the median, the range, and the interquartile range, and then determine if it is skewed or symmetrical. So the median is quartile 2, which is just right here. And so the median here is 22. Now the range is whatever the max is minus the minimum. Max is 28, minimum is 16. Those are the whiskers. 28 minus 16, that's 12. And then the interquartile range is what it asks us to find next. Is quartile 3 minus quartile 1, which is 26 minus 18, as we can see. And so 26 minus 18 is 8. So we found all three of those things. Now it asks us one more question. Is the data skewed or symmetrical? So here we see quartile 2 is much more in the middle of 1 and 3. And the whiskers, there's much more even amount of whisker on each side. I didn't even call it even, actually. 2 amount of whisker on each side. You can literally see the number line here comparatively. And so yes, this data is symmetrical. Or you can just say symmetric if you would rather. Moving on to the next page here. Let's look at shape, center, and spread of the data. And this will help us to look at, once again, whether it's symmetrical or what we call a normal distribution for a curve or a bell curve of data, or skewed, and specifically skewed a certain direction. And so we're going to create a line plot, what's called a line plot, out of data. And so this table here is a random sample of 20 babies born in the hospital. And so we can see babies randomly numbered 1 through 20, because if you're using data, you don't want to just have babies named on there, for example. And their birth month, just correlating to a calendar. For example, January's month 1 and December's month 12. The birth weight in kilograms, and then the mother's age. And and we have one of these line plots for each of these 3 columns. And how you make a line plot is basically each time you see one of these pieces of data, so birth month 5, I'm going to make a little X there for 5, and you want to make so I'll do the same thing for 7. When I see the next piece of data, I see 11, so I'm going to make one for 11. I see 2 as I keep going down the column, and I'm going to make one for 2, and then 10, and 3, and 1. And I just continue going that column, 4, and I see another one for 7. And so what do? I stack it on top. And the goal is to try and make them about the same size and height for each of these. And so as I continue to make this line plot, I do 6, and then 9, and 10 again, and 11. And I just keep working my way through this this table, and at this point I just did baby 14, and I'm on baby 15 now, in case you're curious. Baby 16 and 17. Finally got an August baby there, month 8. Finally got December there, and baby number 19. And so we had a few months twice, but no months more than that. Okay. And then we're just going to do the same thing with birth weight and mother's age. And birth weight, obviously, you see it goes by 0.1s. And so go ahead and feel free to go ahead and make these 2 other line plots, and then we'll pause in the video and then check back in. You're just going to see me kind of go ahead and make them rather quickly, rather than going through the table one by one, but rather using the fact that I know where these already end up. All right, so now we've actually made these line plots. And so now what are we going to do with it? Okay, well, we're going to make or draw a curve over these. And as you can see, some of mine, this one kind of went over the X there, this one went over the X there, and this one didn't touch it. And that was just me making errors when I touched the X. It was an accident. That's okay. And the reason I'm making this curve here wasn't part of the instruction. The line plot is really just the X's. But I'm doing this because I want to talk about distribution, normal versus what we call skewed. Specifically, we're going to talk about directional skewing. And here in this middle one, we see a normal distribution where it's symmetrical distribution where the most is in the middle, and then it tapers off evenly on the left and the right. And we can see that on the plot there, the same number as it goes down on the left and the right. And so this is what we call a normal distribution. I ran out of a space there, but the distribution is ION, and after the T there. And then the mother's age, we can see, is not a normal distribution, but rather we see a lot more over here of younger mothers and a lot less of older mothers over here. And so ignore the fact that there's none over here. That's not our concern. We can just kind of just focus even and zoom in over here on where our focus is. And we just look at where our data is here. We notice, hey, this looks like, it's getting kind of moved or pulled. And so this is what we call skewed. And specifically, we can talk about directional skewed, okay? So you may think, okay, well, there's more of the data here, so do we call it skewed left? And actually, the answer is that it's called skewed right. And the reason why we call it skewed right is because these two data points are what is making the data skew to the right. If these two data points weren't there, we just poofed them away, then all of a sudden, actually I'm going to do that a little bit differently. I'm going to use this with a white marker instead. But if those two data points just weren't there, we just poofed them away, then all of a sudden, this looks far more symmetrical. And so those two data points are quote unquote the culprits, or the main culprits for not being symmetrical. And so we say that those two data points are skewing the data. And so because of it, it's being skewed to the right. It's being pulled to the right, is what we say. And so whatever direction it has more, it's being skewed to the opposite. And this one, we don't have any particular name for that. That is just riding the wave, so to say. One could say, but there's no actual name for that by any means. So what do you notice about the mean and median for the symmetric distribution, which is the baby weights, as compared with the mean and median for the skewed distribution, the mother's ages? And so let's look at the mean and median for these. And so if we find the mean for normal distribution, the mean would be 3.5 if we add all those up and divide by 20. And the median, which I'm going to abbreviate to MED here, would be 3.5. And it didn't ask us to find the mode here, but I'm going to find the mode because it'll ask us to find it later. The mode, which I don't need to abbreviate, that's just one letter, is 35, by the way, as well. Or sorry, 3.5. And I'm going to do the same thing with mother's age because those are the two it asked me to do it for. And the mean is 31.15. The median is 30.5. And the mode is both 29 and 30. So if we compare the 3 measures of central tendency versus the 3 measures of central tendency for the normal distribution versus the symmetrical one versus the skewed distribution, we notice on the normal or symmetrical one that all 3 measures are the exact same. And that will be the case, that either they're the exact same or they're so incredibly close. And here, on the skewed one, the bottom one, they're different. And that'll be the case to where one value is going to be higher or lower than the other. And so that's what we can notice, that the symmetrical one, as the median as are the same, so symmetric has the same mean and median. Skewed has different mean and medians. And then last 4 problems on this page. For each of the following, with which line plot, or write which line plot, is best representative or write neither. And this is why we had to write mode, because it'll be needed on this section, problem 3. And this starts to include birth month as well, potentially. So the median, number 1, is more than the mode. Actually, sorry, this is just between age and weight as well. The median is more than the mode. So between these two. So which one had the case where the median was higher than the mode? Well, that was the mother's age. I'm just going to write age. 2, the mean is equal to the median. Well, that was true with the birth weight, and I'm just going to write weight. Number 3, the mode is equal to the mean. Which one was that true on? Well, that was true on the birth weight. Symmetrical one. And then number 4, the median is less than the mean, and well, that was, once again, the mother's age, where the age had the change between those and the weight did not. All right, on to our next page here, our last page for this section. Let's talk about measures of variation. So we got some definitions to write. Measures of variation now is a value that describes how spread out a data set is. They could also be thought of as measures of dispersion. If you ever heard of someone saying disperse, that just means, spread out. So we're seeing how varied or spread out things are. And so the more clumped together data is versus how not clumped together. And typically speaking, the more clumped together data is, the more reliable that data is. And the more spread out data is, the less reliable that data is how it works. And so variance is one of our measures of variation we'll talk about. Hence, variation, kind of crazy how that works, is the average squared distance. I'm going to rewrite distance there. That's pretty rough, even for me. The average squared distance of each value to the mean. I'm going to write from the mean. Oh, no, to the mean is probably better, actually, now that I think about it. I'll explain why in a little bit. And then standard deviation is our other one we'll be using. There are others, but these are the two primary ones that are used. And this is defined really as the square root of the variance and it is important to note that this is our most useful measure of variation. So this is the one that is used the most often because it is the most useful. You may be wondering, hey, is there a most useful measure of central tendency between mean, median, and mode? And no. It's really just whatever whatever data you're using and how you're using it is what is determined by. You'll see people using whatever best suits their circumstances, honestly, and sometimes whatever best suits their agenda, to be perfectly frank. But with measures of variation, standard deviation just is factually and mathematically the most useful. And so there's this crazy formula here, which I'll actually explain in a little bit. But you won't actually have to know that later. So what do these numbers mean? So I talked about how they're more or less spread out. So a lower standard deviation indicates that, and the same with the variance is true, the values are closer together And the higher standard deviation means the opposite. It means the values, let me do a capital T to match the other one, the values are farther apart. You can also be thought of as more spread out and less spread out. A lower standard deviation means they're less spread out. A higher standard deviation means they are more spread out. It's just different ways of saying the same exact thing, really. So on number 5, we're actually going to find this variance standard deviation doing a formula. And then on numbers 6 through 9, we actually just use our calculator shortcut, which is what you'll be able to do from that point on. So how this formula works, this one is actually easier, believe it or not, because you'll do this one first, which then makes this one easier, even though it's technically more complex. So the variance, this is a Greek letter. It's a Greek letter sigma. And in math, it just means sum. It means add a bunch of stuff up. And so what you do is you take your mean, that was the mu, or the x bar is the same thing, and you take your individual value, whatever your individual value that's so x sub I or x sub 1 or whatever term you have. You subtract your mean, you square it, so it'll always be positive. You add all of those up, and then you divide by however many things you have. So you find the average of all of those. And that's your variance. And then your standard deviation is you just take all of that, which was your variance, and you square root it. Because your variance is, square and standard deviation are squared and square roots of each other. I'll explain it here. So on number 5, find the variance and standard deviation. In order to do that, we first need to find the mean. And so the mean, the x bar or the mu, is 92. We find that by adding these 5 numbers and dividing by 5. And so now our variance, so like let's circle with that little hat squared, is 85, the first number, you could do it in any order, minus our mean, quantity squared. And you could do 92 minus 85. The order doesn't matter because you're squaring it. So whether you get this should be negative 7, quantity squared, or positive 7, quantity squared. The result's either way going to be positive 49. And then you add, hence this sum, the next one. And so you do the next one, 88 minus the mean, 92, quantity squared. And you do the same thing with the next 3 terms. And if there are 12 terms, you do it with 12 terms. If there's 28 terms, you do it with 28 terms. And this formula gets long. Plus 91 minus 92 quantity squared plus 96 minus 92 quantity squared plus 100 minus 92 quantity squared all over however many terms there are again, 5. So we again will divide by 5 just like we did earlier, the average. And so our next step here would be to say, okay, then 85 minus 92 inside the parentheses is 7. So that's negative 7 actually. So negative 7 in parentheses squared plus negative 4 in parentheses squared plus negative 1 in parentheses squared plus 4 in parentheses squared, but the parentheses don't matter there since it's positive, plus 8 in parentheses squared, which once again, parentheses don't matter there, divided by 5. Then, if we actually square all those, we end up getting 49 plus 16 plus 1 plus 16 plus 64, all divided by 5, which that is 146 divided by 5, which is 29.2, which is our standard our variance. And of course, you could actually type all this in your calculator. You just have to be very careful that you put a parenthesis around the whole numerator. And the same thing's true here. You could type any step in your calculator as long as you put the entire parenthesis in your calculator. Not needed here because it's just one term. And then to find your standard deviation, you just take the square root of 29.2, and we're just going to round the 2 decimal places here in this section. And so rounding to 2 decimal places, square root of 29.2 is approximately 5.40. So now let's find out, or actually let me explain the formula a little bit more for any that are curious here. So what this is saying is x sub I, where I starts out as 1, meaning the first term. So x sub 1 meaning the first term, all the way up to x sub n, where n is always just the number of terms, just like it is here. And so in this case, it was x sub 5, because it was all the way up from term 1 to term 5. And so we were saying add up from term 1 to term 5 here. And so we did it from x sub 1 all the way to x sub 5 is what we did. So that's how the formula worked. So now let's figure out the calculator steps. And so what we're going to do is follow these steps that are right here with little screenshots of our calculator, how to do it. But I'm also going to actually showcase my calculator screen here. And so let me go to my camera here so I can do that. And so if I show my calculator screen, I go to Stat. So I click the Stat button here, 2 buttons to the right of alpha. I go to this Edit, which I don't have to push any buttons to go to Edit. I just hit Enter. And then L1 is empty. So I can just type in all my options, all my numbers there into L1. I have to be on these dashes here in order to do that. If I am up here on these, that will give me a problem. Now, if there's any numbers in there currently, so if there are any numbers there, not numbered, but let's say there's, for some reason, a bunch of 5s there for some reason, and I want them cleared out quickly. What I can do is highlight L1, clear, enter, and it clears out the whole thing. So now I type in the list, and the order I type them in doesn't even matter a little bit. So I type in the list, I do 3, enter 4, enter 7, enter 8, 11, 12, 15, 19. So we do need to do repetitions as well there. And then now the instructions say to hit stat again this time. So I hit stat. This time I add it over to calc, and I do 1 bar stats, the first option. It means 1 variable statistics. Statistics only involving 1 variable or 1 list, which is what we're doing. And list 1, L1 is what we're doing. If you were to, for some reason, need to select a different list, you would do that on your calculator here. It is using second, and then our number buttons, so L1, L2, L3, you can see L4, all the way through, L6, using our second button first, but we shouldn't need to do that. Don't need to impact the frequency of the list or anything like that, so we can just go down to calculate. You can just hit enter as well. And on your screen, it tells you up here, X bar, your mean, the sum of the numbers if you were to square them first. I don't remember what that one is off the top of my head, to be honest with you. This is your standard deviation, not your variance. You'd have to square that to get your variance. The number of the numbers, so n, the minimum, quartile 1, if you arrow down there's more, the median, quartile 3, and then we get to maximum as well down there. And we don't see things like the range or interquartile range, but you can find those, and same is true for the mode. But for our purposes here, we really only need to find, we really only need here the standard deviation, because we can use that to then find the variance, which by squaring it. So we need 4.86, blah, 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 or just 4.86 for us, rounding to 2 decimals. So let's go back to our notes. So 4.86 for standard deviation. And if we square that, we get approximately 23.62. I'm going to have you guys pause the video, do the same exact thing on 7, then 8, and then 9, or feel free to do it on 7, check to see what I got, and then do it on 8, check to see what I got, 9, see what I got, and compare. But I'm not going to show my screen on each of these. You don't need to see me typing it in on my calculator with a shaky cam every time. But go ahead. So now that hopefully you've entered those in and found these values in number 7, possibly for 8 and 9 already, depending on whether you went ahead or not. The standard deviation is 4.81. And the variance then squaring that would be 23.14. And the nice part is you can actually literally see that variance is the squared version of standard deviation, since it's just the same symbol, but with the exponent on it. So go ahead and do 8 now if you haven't already. Welcome back again. 8 here. So standard deviation this time is 32.22. Holy cow, it's big. That's because these numbers are really spread out this time. So instead of being numbers that are, only 15 apart, 17 apart from the lowest. Let me try that again. 13 apart. I'll try that again. My goodness. 16 apart from 47 to 63. All of a sudden, we have a number literally doubling. And then some from 63 to 164 from our lowest to our highest. 101 apart. Very, very big gap here. And so our variance then is going to be massive as well. As we square that, 1,038.13. And so we can see our standard deviation went way higher here compared to what it was on 6 and 7. And it shows how much more spread out the data is. So go ahead and do number 9 if you haven't already. All right, on number 9 here, standard deviation this time is much lower at 3.87. The data here is much closer together than it even has been on any of the other examples. So our variance will also be much smaller at 14.98 then. And that wraps up Unit 8, Section 1 of Algebra 2.